The sun you saw today was 8 minutes and 20 seconds out of date. Not approximately. Exactly. If it had gone out while you were making breakfast, you would have carried on for 8 more minutes in full daylight with nothing wrong. And that delay applies to everything you have ever looked at. It gets longer the further away the thing is until you are seeing objects whose light set out before this planet existed. Tonight we drift outward slowly, and at every step the picture gets older. The moon a second behind. The nearest star 4 years. A galaxy you can see with your own eyes, 2.5 million. And at the far end, the oldest light there is. This channel is on Spotify too if you would rather rest your eyes. The link is in the description. Tell me in the comments where you are listening from and what the clock says. Now gently outward. Let your shoulders come down. There's nothing to keep track of tonight. I want to say a word about the shape of this one before we set off, because it is a journey with a very simple rule. We are going to move outward, that is all. One step at a time from the room you are in to the furthest thing anyone has ever seen. And at every single step we will ask the same question. How old is this picture? And the answer will get larger, steadily, without exception, all the way out. It starts in billionths of a second, and it ends in the region of 13.5 billion years. And there is no point along the way where it goes back down. That is the whole of tonight. Distance and age turn out to be two names for the same measurement. And once you see that, the night sky stops being a photograph and becomes something much stranger. A single image assembled from thousands of different moments, none of which is now. We will take it slowly. If you drift off somewhere around the outer planets, the rest of the universe will still be there, and it will still be out of date. Let's begin with something so close it sounds absurd. Look across the room, if there is a room, or just picture the far wall. The light reaching your eye from that wall left it a few billionths of a second ago. That is a real delay. It is not a rounding error or a manner of speaking. Light travels at a fixed speed, and across 4 meters that speed takes about 13 nanoseconds. And so the wall you are looking at is 13 nanoseconds in the past. It has never once occurred to you because 13 billionths of a second is not a duration your nervous system can register. Your brain takes something in the region of 1/10 of a second just to process what your eyes have sent it, which is about 10 million times longer than the light took to arrive. The delay is completely swallowed, but it is there. And the principle it establishes is the whole of tonight. You have never seen anything as it is. You have only ever seen things as they were. Every face you have ever looked at, every book, every landscape. The information arrives late, always without exception, and the amount by which it is late depends entirely on how far away the thing is. At household distances, the lateness is nothing. At the distances we are going tonight, it becomes the dominant fact about what you are looking at. Now, the fact that light travels at all took a very long time to establish, and the story of how we found out is worth telling properly because it was an accident, and the man who noticed was not looking for it. For most of history, the natural assumption was that light is instantaneous. Uncover a lamp and the far wall is lit immediately. Nothing in ordinary experience suggests otherwise. Aristotle held that light is not a movement but a state, and therefore has no speed at all. That view held for around 2,000 years. Galileo doubted it, and in the 1630s described an experiment. 2 people on distant hilltops with shuttered lanterns. The first uncovers his. The second uncovers his the instant he sees the light. the first time's the round trip. It is a reasonable design and it fails entirely, because light crosses a few kilometers in a few millionths of a second, while a human being takes a tenth of a second to react. All Galileo could measure was his assistant's reflexes. He concluded honestly that if light is not instantaneous, then it is extraordinarily fast. The answer arrived in 1676 in Paris from a Danish astronomer doing routine work. Ole Romer was employed at the Paris Observatory, and his task was to time the eclipses of Io, the innermost of Jupiter's 4 large moons. Io goes round Jupiter every 42.5 hours, and on each circuit, it passes into Jupiter's shadow and disappears, then emerges again. This was of practical rather than theoretical interest. A clock visible from anywhere on Earth would solve the problem of determining longitude at sea, which was the great navigational difficulty of the age, and Jupiter's moons looked like exactly such a clock. If you knew what time an eclipse should happen in Paris, and you observed it from a ship, the difference would give you your longitude. The trouble was that the eclipses would not keep to the schedule. Over the course of months, they drifted. For part of the year, they ran progressively earlier than predicted, and for the rest, they ran progressively later, and the total swing was around 22 minutes. Various people had noticed. Rumor worked out what it meant. He observed that the drift tracked the changing distance between Earth and Jupiter as the two planets moved around their orbits. When Earth was approaching Jupiter, the eclipses ran early. When Earth was receding, they ran late. His conclusion was that there was nothing wrong with Io. The eclipses were happening exactly on time. What varied was how long the news took to arrive. When Earth is on the far side of its orbit, the light has to cross the extra width of Earth's orbit to reach us, and the eclipse appears late by however long that crossing takes. In September of 1676, he announced it in the strongest possible way, which is to make a prediction. He told the observatory that the eclipse expected on the 9th of November would occur about 10 minutes later than the table said. It did. Reaumur had demonstrated that light has a finite speed. Christian Huygens took his figures and calculated a value, which came out low, mainly because the true scale of the solar system was not yet well known. But the principle was established, and it was established from a set of timing errors in a table of moon eclipses. The modern figure is exactly 299,792 kilometers per second. And I say exactly because since 1983, the meter has been defined in terms of the speed of light. So the number is now fixed by definition rather than measured. It is fast. It is 7.5 times around the Earth in a second. It is fast enough that for every practical purpose on this planet, it may as well be instant. And it is not instant. And the universe is very large, which is where tonight begins in earnest. Step outside in your mind and look up at the moon. The moon is about 384,000 kilometers away on average, and light covers that in 1 1/3 seconds. So the moon you see is 1 1/3 seconds old. That is the smallest delay in the sky that anyone has ever actually noticed, and the people who noticed it were the ones talking through it. During the Apollo missions, every exchange between Houston and the lunar surface carried a round trip of about 2.5 seconds. You can hear it in the recordings. A question is asked, and there is a pause that is not hesitation, and then the answer comes. Nobody was thinking slowly. The words were crossing the gap. That 2.5 second pause is the shape of tonight, made audible. Keep going. The sun is about 150 million kilometers away, and light takes 8 minutes and 20 seconds to make the trip. which produces the fact I opened with, and it is worth sitting with properly rather than treating as a novelty. If the sun were somehow extinguished at this moment, nothing would happen here for 8 minutes and 20 seconds. The light already in transit would keep arriving exactly as bright in exactly the right color, and the sky would look completely normal. Plants would keep photosynthesizing. Solar panels would keep generating. And then at 8 minutes and 20 seconds, it would go dark, all at once. Gravity would fail at the same moment, incidentally, not before. Changes in a gravitational field also propagate at the speed of light, which was one of the predictions of general relativity, and which was confirmed directly in 2017 when a neutron-star merger was detected in gravitational waves and in light arriving essentially together after traveling 130 million years. So, the Earth would continue orbiting a sun that was no longer there for the same 8 minutes, and then set off in a straight line, outward again. Mars, depending on where the two planets are in their orbits, runs between about 3 minutes and 22 minutes away, which is why every rover on Mars has to be capable of acting on its own. When Perseverance landed in February of 2021, the whole descent took about 7 minutes, and the signal took about 11 minutes to arrive, which meant that by the time anyone on Earth learned the landing had begun, it had already succeeded or failed several minutes earlier. They call it the 7 minutes of terror, and the terror is really about the delay. There is nothing anyone can do. You are watching a recording of something that has already been decided. Jupiter is about 40 minutes away at its closest, and up to 53 at its furthest. Saturn is roughly an hour and a quarter. Uranus about 2.5 hours. Neptune about 4. Which means that when New Horizons flew past Pluto in July of 2015, the images took about 4.5 hours to reach us, and the spacecraft's radio was so faint by then, and its data rate so slow that it took over 15 months to send back everything it had collected in that single afternoon. And out past all of it, Voyager 1 launched in 1977 and now more than 160 times the Earth-Sun distance away, is currently around 23 hours out. A signal sent to it today arrives tomorrow, and the reply comes the day after. The whole solar system, from here to the furthest thing we have built, fits inside about a day of light travel. That is worth pausing on, because we are about to leave it, and the next step is not a small one. The nearest star beyond the Sun is Proxima Centauri, and it is 4.24 light-years away. A light-year is a distance, despite sounding like a time, and it is the distance light covers in a year, which is about 9.5 trillion kilometers. So we have gone from 1 day of light travel to cover the entire solar system out to Voyager, to 4.25 years to reach the very nearest star. That is a jump of more than 1,500 times in a single step, and it is the first honest indication of how empty space is. Proxima is a small, dim red dwarf, invisible to the naked eye, and it has at least one planet in the zone where liquid water could exist. When you look at it through a telescope, you are seeing light that left in the spring of 4 years ago. Whatever's happening there now, you will find out about in 2030. The bright pair next to it, Alpha Centauri A and B, are 4.37 light-years out. Sirius, the brightest star in the night sky, is 8.6 light-years away. The light arriving from it tonight left when a child starting secondary school was in their first year of primary. Vega is 25 light-years. Its light left a quarter of a century ago. Polaris, the pole star, is around 430 light years away, and that number is worth holding on to because the light you see from it tonight left around the time of the first English colonies in North America. Everything you can tell about Polaris by looking is 4 centuries out of date, and these are the near ones. These are neighbors. Now, before we go further, there is a question hanging over all of this that deserves an answer, because I have been reeling off distances all night as though they were obvious. How does anybody know how far away a star is? You cannot go and measure it. You cannot bounce anything off it and time the return except for the very nearest objects in the solar system. Everything beyond that has to be inferred, and the inference is one of the great chains of reasoning in science because each method is calibrated by the one before it. The bottom rung is parallax, and it is the only one that is pure geometry. Hold your thumb up at arm's length and close one eye, then the other. Your thumb appears to jump against the background. That jump is parallax, and if you knew the distance between your eyes and could measure the angle of the jump, you could calculate the distance to your thumb by trigonometry without ever touching it. Do the same with a star. Observe it now, then observe it 6 months later when the Earth has moved to the opposite side of its orbit. The baseline between the two observations is 300 million kilometers, and a nearby star will appear to shift very slightly against the more distant background. The shifts are minute. The first successful measurement was made in 1838 by Friedrich Bessel, working on a star called 61 Cygni, and the shift he found was about 1/3 of an arcsecond, which is the angle a small coin would make at a distance of around 10 kilometers. That gave a distance of roughly 11 light years, and it was the first time anyone had established the distance to a star. It had been attempted for centuries and failed, and the failure had been used as an argument against the Earth moving at all, which we have discussed on this channel before. Parallax has been transformed in the last decade. The European Space Agency's Gaia spacecraft, launched in 2013, has measured positions and parallaxes for well over 1 billion stars with a precision that would let you measure the width of a human hair from 1,000 kilometers away. It has redrawn the map of our galaxy, but parallax has a limit. Even Gaia's precision runs out well before the far side of the Milky Way, because the shifts become smaller than the measurement error. So you need another rung, and the next one is one of the loveliest results in astronomy. And it was found by a woman who was employed as a human computer and paid by the hour. At Harvard College Observatory around the turn of the 20th century, a group of women were hired to examine photographic plates and catalog what was on them. They were not permitted to operate the telescopes. Several of them made discoveries that changed the field. Henrietta Swan Leavitt was assigned to study variable stars, stars whose brightness rises and falls in the Magellanic Clouds. She cataloged them meticulously, and by 1912 she'd noticed something in a particular class of them called Cepheid variables. The brighter ones pulsed more slowly, and crucially, all the stars she was studying were in the same cloud, which meant they were all at roughly the same distance, which meant differences in their apparent brightness reflected real differences in their actual output. So the period of the pulsation tells you the true brightness of the star, which is enormously powerful. Because if you know how bright something really is and you can see how bright it appears, the difference gives you the distance. It is the same reasoning you use when you judge how far away a car is at night from how dim its headlights look, except made exact. Leavitt had found a standard candle. Measure the pulsation period of a Cepheid, and you know its true brightness, and therefore its distance anywhere you can see one. Calibrate the scale using nearby Cepheids, whose distances you know from parallax, and the latter is joined. It was Leavitt's relation that Edwin Hubble used in 1925 to find Cepheids in the Andromeda Nebula and established that it lies far outside the Milky Way, which settled the question of whether the spiral nebulae were separate galaxies. Leavitt died of cancer in 1921 at 53. A member of the Swedish Academy attempted to nominate her for the Nobel Prize in 1925 and discovered she'd been dead for 4 years, and the prize is not awarded posthumously. Beyond Cepheids, the latter continues with a particular kind of exploding star, a type Ia supernova, which detonates at a consistent mass, and therefore a consistent brightness, and which is bright enough to be seen across billions of light years. Those are what the two teams used in 1998 to discover that the expansion of the universe is accelerating. And beyond that, at the greatest distances, we use redshift, which we will come to shortly. So when I tell you that Andromeda is 2.5 million light years away, that number rests on a chain reaching all the way back to Bessel, measuring 1/3 of an arc second in 1838, and to a woman at a desk in Harvard counting the pulses of stars in a photograph. Before we leave the solar system for good, it is worth saying what this delay actually does to people who work with it every day, because it is not an abstraction for them. Everyone who operates a spacecraft lives with a fundamental limitation. You cannot fly it. You can only tell it what to do and then find out afterward what happened. For the moon, that gap is manageable. 2.5 seconds is awkward but conversational, and it is why the Apollo transcripts have that particular rhythm. For Mars, it becomes a different kind of work entirely. Between 3 and 22 minutes each way, so a round trip of up to 44 minutes, which means a rover cannot be driven. It has to be given a plan for the day and left to carry it out with enough autonomy to notice a problem and stop safely rather than continue into a rock. The teams that operate Mars rovers have historically worked on Mars time, shifting their schedule about 40 minutes later each day to match the Martian sol, which is 24 hours and 39 minutes long. People who have done it describe it as a permanent, gentle, unending jet lag and a peculiar sense of drifting away from everyone around them, because within a few weeks you are awake while your family sleeps and you never catch back up. For the outer solar system, the gap becomes strategic rather than operational. When Cassini was steered into Saturn in September of 2017, the spacecraft had already broken apart by the time the final signal reached Earth. Everyone in the control room knew that. The applause and the tears were for an event that had finished an hour and 23 minutes earlier. And for the Voyagers, now around 23 hours out and increasing, every command is a message to a machine that will not receive it until tomorrow and will not be able to reply until the day after. The engineers who operate them are working with equipment designed in the early 1970s, running on a few watts across a gap of nearly 2 light days. And in 2024, they diagnosed and repaired a memory fault on Voyager 1 that took months of exchanges to work through, each one a 2-day round trip. There is a discipline in that which I find admirable. You send the instruction and then you wait, and there is nothing you can do about the interval, and the answer when it comes is already history, and it puts a hard limit on anything further. Any mission to another star would be operated on a delay of years or decades. There would be no controlling it. You would build it, aim it, and spend a lifetime waiting for postcards. Let me give you an image for what the sky actually is, because I think it changes how the rest of tonight feels. Imagine you live somewhere remote, and your only contact with the world is by post, and the postal service is peculiar in one specific way. Every letter takes exactly as long to arrive as the sender is far away. A neighbor's letter arrives the same day. A letter from the next town takes a week. From another country, a year. From the far side of the world, a decade. Now imagine you open your door one morning and the entire day's post is spread out on the step at once. The letter from your neighbor describes what happened yesterday. The one from the next town describes last week. There is one from a friend abroad written a year ago, and one from a cousin on the other side of the world, written when you were a different person entirely. You lay them out and read them together all at once as though they were a description of the world this morning. They are not. They are a composite. Every letter is accurate about its own moment, and none of them is about now, and the further away the sender, the deeper into the past the report comes from. That is the night sky. Exactly that, with no metaphorical softening required. When you look up at a constellation, the stars in it are at wildly different distances, and their light left at wildly different times. Orion is the clearest example anyone can point at. Look at Orion in winter, and you are looking at a shape that seems obviously to be one object, a figure, a unit. It is nothing of the kind. Betelgeuse, the orange star at the shoulder, is around 500 to 600 light years away, and the distance is genuinely hard to pin down because the star is enormous and its surface is uneven. Rigel, the blue-white star at the opposite foot, is around 860 light years. Alnilam, the middle star of the three in the belt, is somewhere around 2000. So looking at Orion, you are seeing light from around the year 1450 in one part of the figure, and around the year 1160 in another, and light from before the Roman Empire in the belt. Those photons left across a span of 8 centuries, traveled entirely separately, and arrived at your eye within the same instant, and your brain assembled them into a single picture of a man with a sword. The constellation does not exist as a thing. It is an accident of alignment, and it is also an accident of timing, and no observer anywhere else in the galaxy would see anything like it. Now, this leads to something people find genuinely unsettling, and it deserves to be handled carefully rather than sensationally. Betelgeuse is a red supergiant. It is enormously large, something in the region of 700 times the diameter of the Sun, large enough that if you placed it where the Sun is, its surface would reach out past the orbit of Mars, and it is near the end of its life. Stars that massive burn through their fuel fast, and Betelgeuse is expected to explode as a supernova, which raises the obvious question. If the light takes 500 or 600 years to arrive, and the star could explode at any time on astronomical scales, then it is entirely possible that Betelgeuse has already exploded, and we simply do not know yet. That is true, and it is worth being precise about how likely it is, because it is usually presented more dramatically than the evidence supports. The best estimates put the explosion somewhere in the next 100,000 years, with a great deal of uncertainty. On that timescale, the chance that it happened during the last 6 centuries specifically is small. Not zero, but small. So the honest statement is not that Betelgeuse has probably already gone. It is that we would have no way of knowing if it had, and that our information about it is 600 years stale, and there is nothing anyone can do about that. There was a period of real excitement about this in late 2019 and early 2020, when Betelgeuse dimmed dramatically, dropping to about a third of its usual brightness, which was easily visible to anyone who knew the constellation. There was widespread speculation that it was about to go. It was not. Follow-up work, including observations with the Hubble Space Telescope, established that the star had ejected a large cloud of material which cooled and condensed into dust, and that dust temporarily blocked part of its light from our direction. The star brightened again through 2020. But when it does explode, whenever that is, the event will already be 600 years in the past by the time anyone sees it, and it will be spectacular. Estimates suggest it would be bright enough to cast shadows at night and to be visible in daylight for weeks or months. It is far enough away to be entirely harmless to us, which is worth saying. And here is the part that I find genuinely strange. Somewhere out there, right now, the light from that explosion may already be in transit, crossing the space between, and there is no way to find out. It will arrive when it arrives. It could be tonight. It could be 40,000 years from now. There is one case where all of this stopped being abstract, and it happened within living memory, and it is the best demonstration anyone has of light delay as a physical fact rather than a thought experiment. On the 23rd of February, 1987, a graduate student named Ian Shelton was working at an observatory in the Chilean Andes. He developed a photographic plate of the Large Magellanic Cloud, the small satellite galaxy visible from the southern hemisphere, and noticed a star that had not been there before. He walked outside and looked up, and it was visible to the naked eye. It was a supernova, the closest one observed since the invention of the telescope, and it was designated SN 1987A. The Large Magellanic Cloud is about 168,000 light-years away, which means the star actually exploded around 168,000 years ago during a glacial period on Earth, long before anything resembling recorded history, and the news arrived on a photographic plate in Chile in 1987. And here is the part that makes it more than an anecdote. 3 hours before the light arrived, 3 separate neutrino detectors on 3 continents registered a burst. Kamiokande in Japan, IMB in Ohio, and Baksan in the Soviet Union. Between them, they caught around 24 neutrinos over about 13 seconds. Nobody knew what it was at the time. The significance became clear only when the supernova was announced. 24 particles. That is the entire haul, and it was enough to confirm the theoretical picture of how a massive star collapses, because the models predicted precisely that a burst of neutrinos should escape first. Why first? Because when the core collapses, the neutrinos are produced right at the center and pass straight out through the star as though it were not there. The light has to fight its way out through the collapsing layers above, which takes hours. So, the neutrinos left the dying star slightly before the light did. Both traveled 168,000 years, and they arrived on Earth 3 hours apart in the order predicted. That is a remarkable piece of confirmation. It also put a very tight limit on the mass of the neutrino, because if neutrinos had significant mass, they would travel measurably slower than light, and the gap would have been much larger than 3 hours after that long a journey. The supernova has been watched ever since, and it has been an extraordinary laboratory. Rings of glowing material have been lit up in sequence as the shock wave from the explosion reached them, each one flaring years after the initial event, which is itself a light delay effect within the object. And there was a puzzle that took decades. The models said a neutron star should have formed at the center, and for over 30 years nobody could find it, hidden behind the dust of the debris. Only recently has evidence for it emerged from infrared observations. So the thing we are watching now in ongoing observations is the continuing aftermath of an event that finished 168,000 years ago. We are receiving the story in real time, in the correct order, delayed by the whole of the journey, which is what tonight is about, demonstrated once close enough to see. Let's keep going outward. Our galaxy is a disk roughly 100,000 light years across, and we sit about 26,000 light years from the center, which means that when you look toward the constellation Sagittarius, toward the heart of the Milky Way, you are looking at light that left around 26,000 years ago. 26,000 years ago on Earth, the last glacial maximum was approaching. There were mammoths. The people painting the caves at Lascaux would not be born for 6,000 more years. The center of our own galaxy is that far out of date, and if you could see a star on the far side of the disk, past the center, its light would have left something like 70 or 80,000 years ago, before our species had left Africa in the migration that populated the rest of the world. There is something in the galaxy that makes this vivid, and it is a specific object. In the year 1054, Chinese astronomers recorded a guest star, a new bright point of light in the constellation Taurus, which was visible in daylight for 23 days and remained visible at night for nearly 2 years. Japanese and Arab observers recorded it too, and there is disputed evidence in rock art in what is now the American Southwest. What they were watching was a supernova, the death of a massive star, and its remnant is still there. We call it the Crab Nebula, and it is about 6,500 light years away, an expanding cloud of debris with a spinning neutron star at its center that pulses 30 times a second, which means the star actually exploded around 5,500 years before anyone on Earth saw it. It happened while the first cities were being built in Mesopotamia, and the news reached China in 1054. And the expansion we watch today, the nebula visibly growing year on year in long-term photographs, is a record of something that finished happening long before there was writing, outward again, and now we leave the galaxy. Andromeda is the nearest large galaxy to our own, and it is about 2.5 million light years away. You can see it. That is the remarkable part. On a clear autumn night away from lights in the northern hemisphere, there is a faint, elongated smudge in the constellation Andromeda that most people mistake for a wisp of cloud, and it is a galaxy containing something like 1 trillion stars. It is the most distant object the unaided human eye can perceive. And the light you would be seeing left 2.5 million years ago. 2.5 million years ago on Earth, our genus was just appearing, Homo habilis. There were no modern humans, no Neanderthals, nothing recognizable as a person. The oldest stone tools we have found are roughly of that age. That light set out before anyone existed to eventually receive it, crossed 24 quintillion kilometers of essentially empty space, and landed on a retina belonging to a species that did not exist when it departed. People have been seeing that smudge for as long as there have been people who look up. The Persian astronomer Abd al-Rahman al-Sufi described it in the 10th century as a small cloud. It was in the sky the whole time, and nobody knew it was another galaxy until 1925, when Edwin Hubble found variable stars in it and used them to measure the distance and settled a debate that had been running for years about whether the spiral nebulae were inside the Milky Way or outside it. They were outside, and the universe got very much larger that afternoon. Now from here on, something changes about the arithmetic, and I want to handle it carefully because it is where most accounts of this subject go quietly wrong. Up to now, I have been treating distance and look-back time as the same thing. 4 light years away means 4 years ago. 2.5 million light years means 2.5 million years ago. That works beautifully out to a certain point, and then it stops working, and the reason is that space is expanding. Here is the difficulty, and it is worth taking slowly because it is genuinely counterintuitive. When light leaves a distant galaxy, it sets off across a certain amount of space. But while it is traveling, the space it is crossing is stretching, which means the light has further to go than it did when it started. It is a bit like walking along a road while the road is being lengthened underneath you, so that a journey which was 10 kilometers when you set out is 12 by the time you finish. That has two consequences, and they pull in opposite directions. The first is that the journey takes longer than the original distance would suggest. The second is that by the time the light arrives, the galaxy that emitted it is very much further away than it was when the light left, because it has been carried along by the same expansion for the entire duration of the trip. So for a distant object, there are 3 different numbers you could reasonably call its distance, and they are all different. There is the distance it was when the light set out. There is the distance the light actually traveled, which is the look-back time multiplied by the speed of light. And there is the distance it is now, which cosmologists call the proper distance or the comoving distance. For the Moon or Proxima or even Andromeda, these 3 are so nearly identical that nobody bothers to distinguish them. Expansion over a few million years across a few million light years is negligible, and in any case, Andromeda is gravitationally bound to us and is not receding at all. It is approaching. But go far enough and they come apart dramatically. Take the most distant galaxy anyone has confirmed, which we will come to properly in a few minutes. Its light traveled for about 13.5 billion years to reach us. That galaxy is now about 34 billion light years away. Those 2 numbers are wildly different, and both of them are correct. The light was in transit for 13.5 billion years. During that time, the space between us and the source kept growing, and the galaxy is now 2.5 times further away than the distance the light covered, which sounds impossible if you think the galaxy has been traveling faster than light. It is not. Nothing is moving through space faster than light. Space itself is expanding, and expansion is not a speed limit thing because nothing is moving relative to its local surroundings. The often quoted number for the size of the observable universe follows from this. The oldest light we can see has been traveling about 13.8 billion years, but the material that emitted it is now roughly 46 billion light years away. And so the observable universe is about 93 billion light years across. That is not a contradiction with the age. It is the accumulated stretching. So from here outward, when I give a figure, I will give the look-back time because that is what tonight is about. How old is the picture? And where the present distance matters, I will say so. Now I have used the word redshift several times, and I owe you an explanation of it, because it is the instrument that measures everything at the far end of tonight, and it is not complicated once you see how it works. The whole thing rests on a discovery from the 1850s. When you pass light from a hot gas through a prism, you do not get a smooth rainbow. You get a set of bright lines at very specific colors, and the pattern is different for every element and is absolutely characteristic of it. Sodium gives a famous yellow pair. Hydrogen gives a red, a blue-green, and 2 violets. Gustav Kirchhoff and Robert Bunsen established this in Heidelberg, and it turned astronomy into chemistry overnight because it meant you could identify what a distant object is made of purely from its light. Those lines are fixed. The hydrogen line that appears at 656 nanometers in a laboratory appears at 656 nanometers in a laboratory anywhere, and always has, because it comes from a specific transition inside an atom, and atoms do not vary. So they are a ruler. Look at a distant galaxy, spread its light out, and find the pattern. Hydrogen is unmistakable, and it is everywhere. You will recognize the arrangement of the lines immediately. But they will not be where they should be. The whole pattern will be shifted toward the red end, all of it together by the same proportion. That shift is redshift, and the amount tells you how much the wavelength has been stretched during the journey, which tells you how much the universe has expanded while the light was in transit. The letter Z is used for it, and the definition is simple. Z is the fractional increase in wavelength. A redshift of 1 means the wavelength has doubled. A redshift of 14 means it has been stretched to 15 times its original value, which is why I said MOM Z14's light left as ultraviolet and arrives as infrared. Stretch ultraviolet by a factor of 15, and that is where it lands. And this is the reason the James Webb Space Telescope was built, to see in infrared. It is not a preference. It is a requirement. The most distant objects have had their light stretched so far out of the visible range that an optical telescope simply cannot see them, no matter how large you build it. Webb also has to be extremely cold for the same reason. Anything warm glows in infrared, so the telescope itself would swamp its own detectors. It sits about 1.5 million kilometers from Earth behind a 5-layer sun shield the size of a tennis court, with the cold side running at around 40 Kelvin. An infrared telescope has to be colder than what it is looking for. Now, there is one more thing to say about redshift, and it is a common confusion worth clearing up. Redshift is often explained as a Doppler shift, like the drop in pitch of a siren as it passes. That is the right analogy for nearby objects moving through space, and it is how we measure the motion of stars in our own galaxy, and it is how Andromeda was found to be approaching rather than receding. But cosmological redshift is not that. The galaxies are not, for the most part, hurtling away through space. The space between us and them is expanding, and the light stretches along with it while it travels. The distinction matters because it is what allows objects to have redshifts, implying recession faster than light without breaking any rule. Nothing is moving through space at those speeds. Space itself is growing, and there is no limit on that because no object is passing anything, which is also why the most distant galaxies we can see are now further away than the distance their light traveled and are permanently unreachable. And yet their light continues to arrive. Right. Onward, and the next step is one of the most audacious decisions in the history of observation. In December of 1995, the director of the Space Telescope Science Institute, a man named Robert Williams, had a block of discretionary observing time on the Hubble Space Telescope. Director's time is a small allocation that the director can spend without going through the usual competitive process. He decided to spend it staring at nothing. He chose a patch of sky in Ursa Major near the handle of the plow, specifically selected because it contained nothing. No bright stars, no known galaxies, no interesting objects at all. It was also at high galactic latitude, meaning we look out of the plane of our own galaxy there, So our own dust was not in the way. The patch was tiny, about 1/24 millionth of the whole sky, roughly what a grain of sand covers at arm's length. A great many astronomers thought it was a waste of a valuable instrument. There was real internal opposition. He pointed the telescope at it and left it there for 10 consecutive days across 150 orbits, accumulating light. The image that came back contained around 3,000 objects, and almost every single one of them was a galaxy. Not stars, galaxies, each one containing tens or hundreds of billions of stars in a piece of sky that had looked completely empty. And because the galaxies in that image are at different distances, they are at different ages. The nearby ones are mature spirals with clear structure. The distant ones are small, blue, irregular, clumpy, obviously in the process of assembling themselves. The image was not a snapshot of the universe. It was a core sample through time. They did it again with better instruments. The Hubble Ultra Deep Field, taken in 2003 and 2004 in a patch in the southern constellation Fornax, over a total of about 1 million seconds of exposure, found roughly 10,000 galaxies. The Extreme Deep Field combined a decade of exposures on a smaller region and went deeper still. And then, in July of 2022, the James Webb Space Telescope released its first deep field image, and it reached further in 12.5 hours than Hubble had managed in weeks. Which brings us to the current record, and to a galaxy with an unlovely name and an extraordinary story. It is called MOEM Z14. It was first imaged by Webb's near-infrared camera on the 16th of May, 2025, as part of a survey program designed specifically to check whether the extremely distant candidates being found were real or were nearer objects masquerading as distant ones. The survey was called Mirage or Miracle, which is where the MOEM comes from. The way you establish a distance like this is through redshift. As light travels through expanding space, its wavelength stretches along with the space. Blue light becomes green, green becomes red, red becomes infrared. The amount of stretching tells you how much the universe has expanded during the journey, which tells you when the light set out. MOEM Z14 has a redshift of 14.44, which means the light arriving has been stretched to more than 15 times the wavelength it had when it was emitted. Light that left as ultraviolet arrives as infrared, which is precisely why Webb was built to see in the infrared and why Hubble could not have found this. That redshift corresponds to a lookback time of about 13.5 billion years, and it places the galaxy as it was roughly 280 million years after the beginning of the universe. The universe is about 13.8 billion years old, so we are seeing this object when it was about 2% of the way through cosmic history. 98% of everything that has happened after that light left. And it is now, as I mentioned, about 34 billion light years away, which is a distance nothing will ever cross. The paper confirming it appeared in the Open Journal of Astrophysics, with a title calling it a cosmic miracle, and it took the record from a galaxy called JADES GS Z40 at a redshift of 14.18. A galaxy called GNZ11, which was the most distant known object as recently as 2022, is now around 14th on the list. That pace of record-breaking is itself the story. Webb has moved the frontier so quickly that lists of most distant objects go out of date within months. And there is a genuine problem attached, which is the interesting part. These early galaxies are too bright. Before Webb, the expectation was that galaxies at that age would be small, faint, disorganized, and rare. What Webb has found is a population of luminous, apparently well-developed galaxies, at ages where the models did not predict them in numbers considerably higher than expected. MOMZ 14 is not a dim smudge. It is remarkably bright, and its light appears to come mainly from stars rather than from a feeding black hole, which would have been an easier explanation. Nobody is claiming the framework is broken. There are candidate explanations involving bursty star formation, unusual initial populations of very massive stars, and lower dust content in the early universe. It is being worked on actively. But the honest statement is that we built an instrument to look at the beginning of the light, and the first thing it told us was that we do not fully understand what happened there, which is, I think, the correct outcome for an expensive telescope. And this gives astronomy something no other historical science has, which is worth pausing on because it is genuinely unusual. Consider how a paleontologist works. They have fossils, which are fragments preserved by chance from creatures that happen to die somewhere that happen to preserve them. Enormous stretches of the record are simply missing, and the whole discipline is an exercise in reconstruction from partial evidence, or a historian working from documents that survived, written by people who chose what to write about events they may not have witnessed. Astronomy is not like that, because looking further is looking earlier. An astronomer studying how galaxies evolve does not have to reason from a handful of survivors. They can look at galaxies at a look-back time of 1 billion years, and 2, and 5, and 10, and directly observe what galaxies were like at each of those ages. Not inferred, observed. And this is exactly how the story of galaxy evolution was assembled. Look at nearby galaxies, and you see mature, well-organized spirals and ellipticals. Look further, and the population changes. Galaxies get smaller, they get bluer, because they are forming stars rapidly, and young stars are blue. They get more irregular, more clumpy, less settled. Mergers become more common because everything was closer together. There is a period at a look-back time of around 10 billion years that astronomers call cosmic noon, when star formation across the universe was at its peak, running perhaps 10 times faster than today. Most of the stars that exist were made around then. Since then, the rate has been falling steadily as the gas available for making stars has been used up, and as expansion has spread everything further apart. The universe is past its peak, star formation is winding down, and will continue to wind down, and almost all the stars that will ever exist already do. We know that not from theory, but from counting at different depths, and each depth is a different epoch. It is as though a paleontologist could look at a hillside and see, at different distances, living animals from every period of the past, still going about their business in the correct order. That is what a deep field image is, a core sample through the history of the universe, with the oldest layers at the back, all visible in a single frame. And the galaxies in it are not arranged by distance for our convenience. They are arranged that way because distance is time. There is one more trick that lets us see further than any telescope should be able to, and it does not involve building anything. It involves using the universe itself as a lens. Einstein's general relativity says that mass curves space-time and light follows that curvature, which means a sufficiently massive object sitting between us and something distant will bend the light passing around it and can focus it exactly as a glass lens does. The effect was confirmed in 1919 when expeditions led by Arthur Eddington photographed stars near the sun during a total eclipse and found their apparent position shifted by the amount relativity predicted. At the scale of a galaxy cluster containing hundreds or thousands of galaxies and an enormous quantity of dark matter, the effect becomes powerful enough to be useful. A cluster in the foreground bends and magnifies the light of whatever is behind it, sometimes by a factor of 10 or 20 or more, and sometimes it produces multiple images of the same background object, smeared into arcs around the cluster. Astronomers call these clusters cosmic telescopes, and they have been used deliberately for decades. The Hubble Frontier Fields program in the 2010s targeted 6 massive clusters specifically to see what was magnified behind them. Webb's very first published image, released in July of 2022, was of a cluster called SMACS 0723, and the arcs of stretched, distorted background galaxies curving around it were the most striking thing in the picture. This has produced results that are otherwise impossible. In 2018, a team using Hubble reported a single star, magnified by a factor of thousands, by a foreground cluster at a lookback time of around 9 billion years. They nicknamed it Icarus. Individual stars at that distance are far beyond the reach of any instrument. It was visible only because a chance alignment focused its light. In 2022, another was reported at an even greater distance, nicknamed Arundel, from an Old English word for morning star, seen as it was less than 1 billion years after the beginning. Webb has since observed it and found evidence it may be a pair of stars rather than one. So the deepest views we have are not purely a matter of instrument quality. Some of them depend on there happening to be a very large mass in exactly the right place, which is a piece of luck we did not arrange and cannot repeat on demand. The universe magnifies its own past for us, occasionally where the geometry happens to work. Before we reach the end of the galaxies, there is one class of object that deserves its own moment because for a long time they were the furthest things anyone could see. And because when they were found, nobody could make sense of them at all. In the late 1950s, radio surveys were turning up sources of radio emission across the sky. Astronomers set about identifying which visible objects they corresponded to. Most turned out to be galaxies. A handful appeared to be stars, which was odd because ordinary stars do not emit that much radio. They were called quasi-stellar radio sources, which was shortened to quasars. The puzzle was their spectra. When you spread out the light of one of these star-like objects, you got a set of emission lines that matched no known element and no known pattern. People spent years on it. In 1963, a Dutch astronomer at Caltech named Martin Schmidt was working on one called 3C273, and he realized what he was looking at. It was hydrogen, perfectly ordinary hydrogen, in the perfectly ordinary pattern. It had simply been redshifted by an amount nobody had thought to consider. The lines were shifted by about 16%, which at the time was an enormous figure, and which placed the object far outside our galaxy at a distance of around 2.5 billion light years. And that created a much worse problem. If it was that far away and still appeared that bright, then it was producing an amount of energy that seemed impossible. Hundreds of times the output of an entire galaxy from something that appeared to be a point. Worse, the brightness varied on timescales of weeks or months, and an object cannot vary faster than light can cross it, which meant the emitting region had to be no more than a few light months across. The energy of hundreds of galaxies, from a region smaller than the distance to the nearest star. The answer, worked out over the following decade, is that a quasar is a supermassive black hole at the center of a galaxy in the act of feeding. Matter spiraling inward forms a disk, and friction heats that disk to enormous temperatures, and the resulting radiation outshines everything around it. It is the most efficient process for converting mass into energy that occurs naturally, considerably more efficient than nuclear fusion. The host galaxy is there, but it is drowned out by the light of its own center. Quasars matter for tonight because they are visible at enormous distances. The most distant confirmed ones are seen at redshifts above 7, corresponding to lookback times of around 13 billion years, at ages of a few 100 million years after the beginning, which raises a difficulty that is still open. Those early quasars imply black holes of hundreds of millions or even billions of solar masses already assembled when the universe was very young. Growing a black hole to that mass takes time, and there does not appear to have been enough of it. There are proposals. Direct collapse of enormous gas clouds into large black holes without forming a star first. Very rapid accretion phases. Seeds from the first generation of massive stars merging repeatedly. Nobody has settled it, and Webb is finding more early black holes than expected, which is deepening the puzzle rather than resolving it. And 3C273 itself, the one Schmidt cracked in 1963, is still there, still bright enough that a good amateur telescope can pick it up, which means that on a clear night, with a modest instrument in a back garden, a person can look at light that left a feeding black hole 2.5 billion years ago, when the most complex life on Earth was single-celled, and there is an attempt underway to see into the dark ages themselves, which sounds impossible given that there was nothing emitting light, and which turns on a technicality of atomic physics. A neutral hydrogen atom has a proton and an electron, and both of them have a property called spin. Those spins can be aligned or opposed, and the aligned state has very slightly more energy. Very slightly. The energy difference is tiny, and an atom in the higher state will eventually flip to the lower one and emit a photon carrying that small difference. The wavelength comes out at 21 centimeters in the radio band. The transition is extraordinarily unlikely for any individual atom. Left alone, a hydrogen atom would take something like 10 million years to flip, which would make it useless, except that the early universe was made almost entirely of neutral hydrogen in quantities so vast that even a transition taking 10 million years per atom produces a detectable signal in aggregate. So the dark ages were not entirely dark after all. They were dark in visible light, because no star existed. But the hydrogen filling the universe was quietly emitting at 21 centimeters the whole time. And that signal, redshifted by everything since, should be arriving now at wavelengths of a few meters in the low-frequency radio band. Detecting it is brutally difficult because our own galaxy emits at those frequencies thousands of times more strongly, and human radio transmission floods the same band. It is a signal 100,000 times fainter than the foreground it is buried in. Several efforts are underway. Large arrays of simple antennas spread across radio-quiet regions of Australia and South Africa. The square-kilometer array under construction is designed partly with this in mind. There was an announcement in 2018 from an experiment called EDGES, reporting a possible detection of the signal from the era when the first stars switched on, and the shape of it was stranger than the models allowed. It has not been independently confirmed, and a later experiment failed to reproduce it, so the honest position is that it remains unsettled, and there are proposals. serious ones, to do this from the far side of the moon. The lunar far side is the only place in the inner solar system permanently shielded from Earth's radio noise, because the moon itself blocks it and it has no atmosphere to interfere either. It may be the quietest radio location available to us, and there are concepts for arrays of antennas laid out across a crater floor there. If it works, we would have an image of the universe during the period when there was nothing to see. Not by catching starlight, because there was none, but by listening to hydrogen, which would fill in the one remaining gap in tonight's ladder between the microwave background and the first galaxies. Keep going outward and something changes. The galaxies thin out. Look far enough back and you reach an age when galaxies had not yet formed, and there is nothing to see because there was nothing there to emit light. That period has a name: the cosmic dark ages. Here is what the sequence looks like, in order. After the universe became transparent, at about 380,000 years, it was filled with a fierce glow, and we will come to that glow in a moment because it is the end of tonight's journey. That glow faded as space expanded and stretched it. Red, then deep red, then infrared, then out of the visible range entirely. And then there was nothing to see. No stars had formed. The universe consisted of neutral hydrogen and helium, spread almost evenly, cooling and dark, with the faint irregularities in it being pulled together very slowly by gravity. That went on for something in the region of 100 million years, possibly longer, and it is the only period in cosmic history when the sky was genuinely, completely black. Then the first clumps collapsed far enough to ignite, and the first stars began to shine, and everything since has followed from that. Those first stars are thought to have been unlike anything now. They formed from pure hydrogen and helium, with no heavier elements, which changes how a collapsing gas cloud cools and fragments, and the models suggest they were enormous, tens or hundreds of times the mass of the sun, burning blue hot and living only a few million years before exploding. Nobody has seen one. They are the great prize of this field, and they are just beyond reach. MOAM Z14, at 280 million years, is close to the era, but is a galaxy, not an individual first-generation star, so the deep field images have a flaw in them. Look deeper and deeper, and the galaxies get smaller and stranger, and then they stop, and behind them is the dark, which means that if you kept looking outward, you would eventually see nothing at all, except that you would not, because behind the dark ages there is something else, and it is the oldest thing that can be seen, and it is the natural end of this journey. Go back further still, before any star, before the dark, and the universe was hot, not warm, hot enough that atoms could not hold together. Electrons had too much energy to stay bound to nuclei, so matter existed as a plasma of bare nuclei and free electrons moving separately. Free electrons scatter light extremely efficiently. A photon in that environment would travel a very short distance and be knocked sideways, then again, and again, endlessly. Light could not move in a straight line for any useful distance. The universe was opaque, blazing bright and impenetrable in the way the interior of the sun is opaque. Then it expanded, and expanding gas cools, and at around 3,000 Kelvin something changed. That is cool enough for nuclei to capture and hold electrons, and across a relatively brief interval, most of the free electrons in the universe were taken up into neutral hydrogen and helium. That happened about 380,000 years after the beginning, and it is called recombination. and the instant the free electrons were gone, the fog lifted. Photons that had been bouncing every few centimeters suddenly found nothing in the way, and they set off in straight lines, and most of them have been traveling ever since. They are still arriving. That is the cosmic microwave background, and it was found by accident in 1964 by two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, who spent the best part of a year trying to eliminate a faint hiss from a horn antenna. They checked the electronics, they evicted a pair of pigeons that had been roosting inside, they cleaned the horn and taped the rivets, and the hiss did not budge. Meanwhile, a group at Princeton, 60 kilometers away, was building an instrument to look for exactly that signal, having reconstructed a prediction made in the 1940s by George Gamow, Ralph Alpher, and Robert Herman. The two groups were connected by a mutual acquaintance and published side by side in 1965, and Penzias and Wilson received the Nobel Prize in 1978. Here's what it means for tonight. That light comes from a surface, and I want to be precise about what kind of surface, because it is not what the word suggests. Recombination happened everywhere at once, throughout the entire universe. There is no special location out there where it occurred. What makes it a surface is that looking outward is looking backward. Look further and you look further back, and there is a particular distance at which you are looking back exactly to that moment. And that distance is the same in every direction because you are at the center of your own view. So the surface of last scattering is a sphere centered on you, made not of matter but of a moment in time. Every observer everywhere has their own, centered on themselves, made of different photons that had their final collision in a different place. And it is a wall, not a wall in the universe, but a wall in what light can tell you. Behind it, the universe was opaque, and no photon from earlier than that can reach anybody, ever, because they could not travel in straight lines. Its look-back time is about 13.8 billion years, minus 380,000, which at this scale is a rounding error. Its temperature, when it was released, was around 3,000 Kelvin, roughly the color of a dim red star. It has since been stretched by a factor of about 1,100 by the expansion of space, which has cooled it to 2.725 degrees above absolute zero and shifted it into microwaves. It fills the entire sky in every direction with no gaps at all. It is passing through the roof above you and through your body right now at a rate of hundreds of trillions of particles of light every second. You have almost certainly seen it indirectly. Old analog televisions, tuned between channels, showed a snowstorm of static, and a small fraction of that static, in the region of 1%, was the cosmic microwave background arriving at the aerial. That is the oldest light there is. Nothing older can be seen because there was no older light that could travel. So our journey outward has an end, and this is it. 13.8 billion years of look-back time, and then a wall, and behind the wall, an opacity that no telescope will ever penetrate, except that light is not the only thing that carries information. And there are two other windows, and both of them see past the wall. The first is neutrinos. A neutrino is a particle with almost no mass and no electric charge, and it interacts with matter so feebly that it is difficult to convey. A neutrino could pass through a light year of solid lead with a reasonable chance of not touching anything at all. That property makes them almost impossible to detect, And it also makes them the best messengers in physics because nothing stops them. And here is what matters for tonight. Neutrinos stopped interacting with the rest of the universe far earlier than light did. Light was trapped in the plasma for 380,000 years. Neutrinos decoupled at about 1 second after the beginning, when the universe was still unimaginably hot and dense, because even at that density, neutrinos barely notice matter, which means there is a cosmic neutrino background, exactly analogous to the microwave background, released when the universe was 1 second old, rather than 380,000 years old. It is out there. It fills space. Current estimates put the density at something like 336 of these relic neutrinos per cubic centimeter, everywhere, including in the room you are lying in. They have been traveling since the first second. We have not detected them directly, and it is one of the hardest problems in experimental physics because expansion has cooled them to under 2 Kelvin, which leaves them with so little energy that no existing technique can catch one. There are experiments being designed with that goal, but nobody has done it. And yet we know they are there because their gravitational influence in the early universe left a measurable imprint on the cosmic microwave background and on the pattern of galaxies. The signature is unambiguous. The particles themselves are just out of reach. If we ever do detect them, we will be looking at a picture of the universe at 1 second old. The second window is stranger still. Gravitational waves are ripples in the geometry of space-time itself, predicted by Einstein in 1916 and detected directly for the first time on the 14th of September 2015 when the LIGO detectors in the United States registered the merger of 2 black holes about 1 3/10 billion light years away. That detection required measuring a change in length smaller than 1,000th of the width of a proton across a 4-kilometer arm, and gravitational waves pass through everything. Matter is essentially transparent to them, including the hot, dense plasma of the early universe, which means primordial gravitational waves generated in the first fraction of a second would still be out there and would carry information from far earlier than 1 second from the period of inflation itself at something like 10 to the minus 35 seconds. Nobody has detected those either. The signal is expected to be extraordinarily faint, and there was a false alarm in 2014 when a team announced a detection which turned out on further analysis to be dust in our own galaxy. But if it is ever found, it would be a picture from the first instant. So the wall we hit a few minutes ago is a wall for light specifically, and there is at least the possibility of seeing past it by other means. That is, I think, one of the more hopeful facts in physics. The limit is not on knowledge. It is on one particular messenger. There is a consequence of everything we have said tonight that points forward rather than back, and it is the melancholy one, so I will be brief about it and then leave it. We have established that looking outward is looking backward, and that the further you look, the older the picture. There is a corollary. For the most distant things we can see, we will never see anything newer. The expansion of the universe is accelerating. That was established in 1998 by 2 competing teams measuring the brightness of type Ia supernovae in distant galaxies, and it was so unexpected that both spent a long time hunting for errors before publishing. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the Nobel Prize for it in 2011. Whatever is driving it, and dark energy is a name rather than an explanation. The effect is the galaxies beyond a certain distance are being carried away faster than their light can close the gap. That boundary is called the cosmic event horizon, and things cross it continuously. Once a galaxy is crossed, its light from before the crossing keeps arriving, and will keep arriving for a very long time, redder and dimmer and slower. But nothing it does afterward will ever be seen from here. The overwhelming majority of the galaxies visible in a deep field image have already crossed. We are watching their past, and there will never be an update. Mom Z14 at 34 billion light years crossed long ago. What we see of it is what we will always see of it. The rest of its life, the whole of it, has already happened somewhere out there, and none of it is coming. And it goes further. Over tens of billions of years, more and more will cross. Galaxies will redden and dim and eventually fade from view entirely, one by one, until the local group has merged into a single elliptical galaxy, and there is nothing else visible at all. The microwave background will stretch, too, further and further until no instrument could detect it. So there will be astronomers in some enormously distant future looking out at a sky containing their own island of stars and nothing beyond it. No other galaxies, no background glow, no redshift to measure, and no expansion to notice. They will have every reason to conclude that their galaxy is the whole universe, static and eternal, and no possible way to discover otherwise. The evidence will not be hidden from them. It will be gone, which makes this a specific and rather fortunate era, late enough that there are stars and planets and eyes, and early enough that the history is still arriving. I do not think that means anything cosmic about us. It is simply where we are standing, and it is a good place to be standing if you want to know things. There is something worth saying about how the light is actually caught, because the deep field images are not photographs in any ordinary sense, and the difference matters. Your eye does not accumulate, it refreshes. The retina integrates light over something in the region of 1/10 of a second, and then starts again, which is why you cannot stare at a faint star and gradually see it more clearly. Whatever arrives in that 1/10 of a second is all you get over and over. That sets a hard floor on what a person can see. A fully dark adapted eye can respond to a handful of photons, which is astonishing sensitivity, and it still cannot see a galaxy at a lookback time of 13 billion years. Because in 1/10 of a second, essentially nothing arrives from there. A telescope does two things about this, and the second is the important one for tonight. The first is aperture. A larger mirror catches more light in proportion to its area, so doubling the diameter quadruples the light. Webb's mirror is 6.5 meters across, made of 18 gold-coated hexagonal segments, folded for launch and unfolded in space, with a collecting area around 6 times Hubble's. The second is time. A detector, unlike an eye, can keep counting. Leave it pointed at the same patch and photons keep landing and the total keeps rising, and eventually a signal that would be invisible in any single moment accumulates into something clearly there. The Hubble deep field was 10 days of accumulation. The ultra deep field was around 1 million seconds. Some observations run for weeks of total exposure, assembled from many separate visits over months, which means the image you eventually look at is not a moment. It is a summation, and the photons in it did not arrive together. They trickled in individually, one at a time, spread across days or weeks, each one having traveled for billions of years to land on a particular pixel. For the very faintest objects in those images, the arrival rate is genuinely that low. Individual photons, minutes or hours apart, from a galaxy that assembled itself before the Earth existed. There is something in that I find quietly moving. The light was not sent to us. It went out in every direction as light does, and the overwhelming majority of it is still traveling and will never encounter anything. An unimaginably small fraction of it happened to be aimed at a 6-meter mirror 1.5 million kilometers from a small planet 13 billion years later. And a detector was there, cold and patient, counting. Now let me come back and say plainly what all of this adds up to, because there is a conclusion here that I find genuinely reorienting. No telescope has ever seen the present, not once in the entire history of astronomy. Every image ever produced of anything beyond the Earth is a historical document, and the further away the subject, the older the document. There is no instrument that could fix this, and there never will be, because the limitation is not technological. It is a property of the universe. Information does not travel instantaneously, and everything you know about anything distant is news that took time to arrive, which means the phrase, "what is happening out there right now," has no clear meaning at cosmological distances. That sounds like a philosophical flourish, and it is not. It is a technical consequence of relativity. In everyday life, we assume that now is a universal thing, a moment shared by everything everywhere. Special relativity says otherwise. The set of events that count as simultaneous with your now depends on your own motion, and different observers moving at different speeds will disagree about which distant events are happening at the same time. For nearby things, the disagreement is unmeasurably small. Across billions of light years, it is enormous. So asking what a distant galaxy is doing now is not a question with a single answer, even in principle. There is no shared present to refer to. What there is instead is a light cone. Every event has one, the set of all points from which light could have reached it. Your past light cone is the complete list of everything you could possibly know about, and everything outside it is, at this moment, unknowable to you. The night sky is a picture of your past light cone. That is all it can ever be. A surface through space-time, not a snapshot of space. And this leads to the thing I actually find beautiful about it, which is the flip side of everything we've said. We usually think of the past as gone. That is what past means. It happened, and it is over, and it is not available, but the past of the universe is not gone. It is arriving continuously from every direction at 300,000 kilometers per second, and it will keep arriving for as long as there is anything here to receive it. The light from the early universe is still coming in. The light from galaxies that assembled themselves when the cosmos was 1/50th of its present age is landing on detectors in Chile and in orbit tonight. Nothing about it has been lost, which means that looking outward is the only form of time travel that actually works, not metaphorically and not as a figure of speech. You cannot go to the past, you cannot send anything to it, you cannot change it, but you can observe it directly in detail with instruments at your leisure, and it is happening constantly, and nobody thinks it is remarkable. Every observatory on Earth is a time machine that only points one way, and the further you look, the further back you go, which means the universe hands you its own history in order, arranged by distance, free of charge, permanently on display. You do not have to reconstruct it from evidence the way a geologist or a historian does. You look at it. There is one more thing to say before we go quiet, and it is about the other direction. We have spent all night looking outward and backward. It is worth spending a moment on the fact that the relationship runs both ways. Anyone out there looking back at us sees us late by exactly the same amount. If there were an observer with a very good telescope in the Andromeda Galaxy, and they were watching Earth tonight, they would be watching a planet 2.5 million years in the past. No cities, no agriculture, no people in any modern sense. Early hominins with stone tools on a continent that has since moved. An observer 65 million light years away, watching now with an impossible instrument, would see the asteroid arriving at the Yucatan. An observer 400 light years away would be watching Galileo point a telescope at Jupiter. An observer 80 light years away would see the Second World War ending. And this has a curious consequence that gets talked about in the search for other civilizations. Our own radio transmissions have been leaking into space since roughly the 1920s, which means the sphere of Earth's broadcasts is currently about 100 light years in radius. That sounds enormous, and it is nothing. 100 light years is a tiny neighborhood in a galaxy, 100,000 light years across. The bubble of our broadcast covers something in the region of 100,000th of the volume of the Milky Way. And those signals are weak. Ordinary broadcast transmissions become undetectable against the background noise at surprisingly modest distances, and the more efficient our technology gets, the less we leak, because efficiency means not wasting energy radiating in directions nobody is listening. So the honest picture is that we have been visible faintly to a small nearby region for about a century, and even there we would be hard to notice, which is worth holding alongside the rest of tonight. Not only is everything we see out of date, everything anyone could see of us is out of date by the same rule, and there is no way around it for anybody. Every civilization anywhere in the universe, if there are others, is in exactly the same position. Each one sitting at the center of its own sphere of arriving history, seeing everything late, seen by everything late. Nobody anywhere has ever had a current picture of anything far away. Let me draw it together gently because it is getting on. Here is the ladder we climbed tonight. The wall of your room, 13 billionths of a second ago. The moon, 1 1/3 seconds. The sun, 8 minutes and 20 seconds, and every warm afternoon you have ever had was warmed by light that left before you noticed it. Jupiter, 40 minutes. Neptune, 4 hours. Voyager, most of a day. Proxima Centauri, 4 1/4 years. Sirius, 8.5. Polaris, 4 centuries. Betelgeuse, 500 or 600 years, and possibly not there at all. The center of our galaxy, 26,000 years back when there were mammoths. Andromeda, 2.5 million years before there were people, and you can see it with your own eyes. The deep field galaxies, billions of years, most of them older than this planet, many of them older than this galaxy in anything like its present form. Moam Z14, 13.5 billion years, seen as it was when the universe was 2% of its current age, and now 34 billion light years away, and permanently beyond any possible reach. And the microwave background, 13.8 billion years, arriving from every direction at once, released when the universe first became transparent, and passing through you continuously. Every one of those is a real measurement. Every one is a picture from a different moment, and your sky contains all of them simultaneously, layered on top of one another, presented as though it were a single image of a single instant. It never was. There is no such image, and there cannot be. Take a slow breath now if you are still with me. You are lying in a room, and the light in it left the walls a few nanoseconds ago. Above the roof, if the sky is clear where you are, there are points of light that set out 4 years ago and 40 and 400, and some that left before there was writing, all of them arriving together tonight, in the same second, on the same small patch of ground. The nearest large galaxy is up there somewhere, a faint smudge that departed before your species existed, and it has been traveling the whole time through nothing, without slowing, without changing, waiting for something to land on. And beneath all of it, underneath every star and every galaxy and every gap between them, filling the whole sky in every direction without a single break, is a glow that was released 380,000 years after the beginning of everything, when the universe first cleared, and it has been coming ever since, and it is arriving now through the roof, through the room, through you, at hundreds of trillions of particles a second. None of it is happening now. All of it is arriving now. That is not a loss, and it is not a trick, and it is not a limitation to be worked around. It means the past is not gone. It is in transit. It is the only thing that ever reaches us, and it has been reaching us reliably for as long as there have been eyes here, and it will keep reaching us long after. You do not have to go anywhere or do anything. The history of the universe is arriving at your window tonight, in order, oldest at the back. It has been doing this every night of your life. Sleep well.